I have a pen. I have an apple. Apple pen. I have a magnet. I have some electric. Electromagnetism. Hello everyone. Welcome to the second part of Maxwell equations. And let's continue our journey on reviewing the secret between electricity and magnetism. In the previous video, we learned that the voltage is actually an integral between B and A, E dot dl. And we particularly introduce what is meant by the term of closed loop integral. We say the closed loop integral around any point apart from the voltage source is zero. But when it comes to the voltage source, the closed loop integral around the voltage source is actually the source voltage being generated. So the left-hand side of this question, we can also say is equal to V source, which means how much voltage is generated across the source. But what about the right-hand side of the equation? Yeah, and we say all of these three implementations are related to the left-hand side of this equation. And in this video, we are going to talk more about the right-hand side of this equation, which is related to a change in magnetic field. Remember, in the first slide, we say a moving magnet can induce a charge to flow, which means it will induce a kind of voltage, because voltage is the prerequisite assumption of a current. Only when we have voltage, we can have a current, which means when we have a charge to flow, we have a current, we definitely have a voltage. So the first one is actually related to the left-hand side. So the right-hand side should be related to a moving magnet, which means a change in magnetic field. However, we are going to dig deeper into this concept and explain how we can use a mathematical equation to calculate a specific voltage generated with a magnetic field. And we'll break it down into simple parts. So starting with magnetic flux density, which is a B here. Recall from A levels, we've talked about magnetic flux, which is the number of magnetic field lines passing through a certain area. For example, let's take this area. We can see 3 magnetic field lines across it. And we take this area, there's only 1 magnetic field line through it. So we can say the first area, this one, has a larger magnetic flux than the second one. And the magnetic flux is actually related to the two things. The first one is the area. If we take a larger area, right, we definitely have a larger magnetic flux when everything else is the same. And also, it's related to the magnet. On the right-hand side, we have a stronger magnet. Even though we have the same area, the right-hand side magnet will have a higher magnetic flux because it has a higher magnetic flux per unit area. Okay, this introduces another concept called magnetic flux density, which is shown here. It's B. The magnetic flux per unit area perpendicular to A. So in this case, we will get rid of the area's influence. We're only considering unit area, which is kind of similar to electric field strength, which is per unit charge, and here is per unit area. And it has a unit of Tesla. And I forgot to speak about that magnetic flux. It has a unit of Weber, short written as WB, and Tesla is T. So in order to write down the magnetic flux density with mathematical equations, we write B is equal to phi B over A when the phi B is normal to A. Okay, there is an important thing. The magnetic flux has to be perpendicular to the area to be calculated directly with this formula. So we can also arrange this formula into another one, which is phi B is equal to BA, which we just put the A on the left-hand side, but provided B, the magnetic flux density, is normal to the area A. But what will be the case if B is not normal to A? Say B is somewhere random. Let's consider two extreme cases first. In the first case, the magnetic flux density is perpendicular to A. And in this case, we know we have BA. And in the second case, it is parallel to the magnetic flux density. The area is parallel to the magnetic flux density. And in this case, we have phi b is equal to 0 because literally no magnetic flux lines, magnetic field lines passing through the area. So we have a 0. In 99% of the cases, the area we have is at an angle with the magnetic field lines. It's not perpendicular, but it's not parallel to. So we can generalize these cases into two parts. Yeah, in general cases, we can decompose the magnetic field into two parts. So the B field, we can decompose it into two parts. Phi is equal to BA when B is normal to A. So B is a vector. We decompose a vector into two components. One perpendicular to the area A and one parallel to the area A. For the one perpendicular to the area A, phi B is equal to BA. And for the one parallel is 0. Or we can also write it down as another formula, which is BA times cosine theta. So B times this cosine theta, then we have this vertical component, because this is the only component that actually counts. So B times cosine theta, we have the B here, and then we times the area, which is kind of similar to the work done formula before, where theta is the angle between the magnetic field lines and its perpendicular. Or we can also write it down as a vector dot product, B dot A. But in this case, normally area is a scalar because we say it only have magnitude, no direction. Yeah, we only say how large is the area, but we never say the area is pointing somewhere. We never say that. However, we can arbitrarily give the area a direction to change the area to a vector. And for example, this area, we choose upward as the positive direction. And then we can have a vector product form as well. Sorry, vector dot product form as well, which connecting back to what we have learned in the last session. However, there will be the same thing occurs. The previous equation, which is assume B is a constant everywhere. And in this case, however, in most of the cases, the magnetic flux density is no longer a constant. So we need to use integration. So in order to calculate the phi value, which is equal to B dot A, right? That means crossing the area A, it has a constant B over it. Like say the first example, we take this rectangular square. Everywhere on this square has a constant B. So we can just directly times B with the area A. However, in the case around a magnet, the area across the same area A, the magnetic flux is no longer a constant. Okay, so somewhere it's larger, somewhere it's smaller. So we can't use this directly vector dot product form anymore. We need to use integration as before. So how do we do this? We assume when the area A1 is very small, the magnetic flux density B1 doesn't change. So say this small A1 and the B1 is the same. Then at this instance, phi B1 is equal to B1 times A1. Okay, we can still use the formula before, which is equal to B times A, which is the vector dot product form. Remember, it's not a scalar product. It's a it's not a normal product. It's a vector dot product form. And then we can repeat the same thing for B2, B3, and B4 with area A2, A3, and A4. And then we sum it up, which can also be written down with summation form. Sigma I is equal to 1 to n B times A. And we do the same thing. When A is infinitesimally small, the equation will become an integral, which is phi B is equal to B dot ds, a vector product between B and S, integrated over a surface S. In this case, because we are integrating over an area, we are no longer integrating it within a line. Let's say 2 points. We are no longer integrating between points. We are integrating across a certain area, S. So the integral form will change to an S here. Okay, we have kind of the right-hand side of the equation, and let's compare between them. We'll see they have fairly similarities. We both have b dot ds, b dot ds. However, the integral is not the same. This is a surface, but this is what this means. We can guess it's like a closed surface, but what is open surface? Okay, let's have a look. So in this case, it actually means it's a closed surface integral. But before introducing that, we'll see, okay, closed surface. A closed surface encloses a finite volume. So for example, a whole eggshell, like we have an egg from Tesco, and that's a closed surface. Or a sphere, like football. I know England is famous for football, and the football is actually a sphere. So it is a closed surface, like shown here. And on the contrary, the open surface doesn't enclose a finite volume. Say, for example, a lampshade. A lampshade, we have like a certain shape like this, right? If I put a point, I put my finger inside, I can literally take it outside very easily. So it's not fixed, it's not closed, it's not a fixed volume. And in this case, it's called an open surface, like shown here. Half an eggshell, if you punch the egg and put it into the pan and you break it, the half of the eggshell is not a closed surface, it's an open surface, like shown here. So let's look back to our Maxwell equations. In the right-hand side, this circle is actually means integrating over a closed surface. So basically, you have to choose a certain finite volume to integrate it. Yeah, and I will turn off the camera. Sorry, I can't. It said total magnetic flux through a fixed area. Yeah, so it has to be a closed loop. Yep, closed surface. And the left-hand side is actually a representation of voltage. Yeah, through a closed surface, sorry. But in connection between these two, we also see a term, division term shown here, which is actually the rate of change of, right? So we will see how this actually works in a single wire loop. So imagine we have a wire here, and we put a magnet here, and we basically do nothing. There will be no voltage generated in this wire. Why? It's because there is no change in the total magnetic flux through the closed surface. The magnetic flux doesn't change in this case, so we never generate any voltage at all. However, if I shake the magnet up and down, and in this case, the total magnetic flux through the closed surface, the total magnetic flux through this wire loop is going to change. And then with a change in magnetic flux, we have a voltage. So that's why some textbooks say when we have the wire cutting magnetic flux lines, like what's shown up here, it will generate a voltage because it's actually changed the total magnetic flux through this closed surface. Okay, so remember, if we sit still and do nothing with a magnet, it won't gonna generate any voltage. You need to pay work. Okay, you need to do some work, move the magnets around, and then you will see the voltage. Let's think back to the three examples we had before. For example, like crosstalk. Imagine the oldest telephone wires is actually made up of two wires. The telephone lines is composed of two wires. And it is originally a sinusoid signal, like in this one. However, there is some electrical interference, that's the magnet moving up and down here. And this will make the signal noisy because it's supposed adding up some voltage on it randomly. And it looks like some noise onto it. And that's how noise is being generated. This phenomenon is called crosstalk. And for the second case, the wireless charging is actually some similar principles. Let's see the photo downwards. We have an alternating current into the primary coil, like the coil on the left-hand side here. It will create a changing magnetic field which these magnetic field lines is varying. So connecting back to this equation, the total magnetic flux through a closed surface, we take the surface as all the wires, blah, 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 down to, say, for example, your phone here. This loop, this area loop is actually changing. So in this case, we have a changing total magnetic flux. So the rate of change is not zero anymore, and then we induce a voltage. The actual implementation of the design of wireless charging is actually similar to the top diagram instead of the bottom. We just punch down all the wires into a single plane. And the same equation can be used to explain the principle behind the power generator as well. Let's see this GIF as an example. The area inside of this, I will draw it here, inside of this rotor is what we taken as a closed surface. When we take this closed surface, we rotate it around in between of the North Pole and the South Pole, we are actually creating a changing in the total magnetic flux through the area. We have some cases when it's perpendicular to the magnetic field lines, and in this case, we have the largest magnetic flux. And when it's parallel to the magnetic field lines, it has a zero magnetic flux through this area. So, which means the magnetic flux is varying between maximum and zero, and then from zero back to maximum again. So we have a changing magnetic flux, and then we have a voltage generated. So crosstalk, power generator, and wireless charging, they have something in common. They all have the left-hand side, which have some voltage being generated, and they also have a changing magnetic field as well. However, for the last part about the Maxwell equations, we'll focus on this minus sign. This minus sign means the induced voltage is opposing the changing magnetic flux. So for example, when we drop down a magnet through this tube, it's taken a very long time, right? However, when we drop an iron ball, we get it instantly. It's even not shown in the photo. It's very fast. So if we take two screenshots, if we drop an iron ball inside of a copper tube, it falls with 0.02 seconds. And if we take a special, like a magnet, same size as an iron ball, it will fall with approximately 4 seconds, which is almost 200 times as the previous case. Why is that? It actually can be explained with Maxwell equation, because the voltage generated is opposing the motion of the magnet, which is opposing the change to it. The magnet tries to create a voltage in the copper tube because it's closed loop. So the magnet, when it passes through the copper tube, it will generate a voltage, and the voltage in a closed loop, it will create a current, and this current will act back onto the magnet, which creates a resistive force onto it, which is F opposed. That's where this minus sign coming from. It's opposing the changing of the magnetic flux. So this magnet tries to change the magnetic flux across this copper tube. So the copper tube will resist against it by creating a force opposite to it. So that's where this minus sign is coming from. This equation can be also described as Lenz's law. In the final section of this video, I want to emphasize that energy is not free. Just because of the Lenz's law, when we have the power generator, taking this instance as an example, when we rotate anti-clockwise, there will be a force acting on the magnet to prevent it actually from rotating. So when this coil rotating around this magnetic field anti-clockwise, it will generate a current in the loop. And the generated current will generate a magnetic field too. When these two magnetic fields interact, they tend to oppose one another. So to stop the motion from it, this actually makes sense. If we rotate this coil wire and then it's just generating the voltage without slowing down, then we actually have a permanent machine, free energy. We just turn the coil around, nothing happens, and then it will be electricity coming out, powering up our laptops, our buildings, our cars, forever and ever, which is totally impossible, right? So the current generated in a coil will induce a varying magnetic field. The current generated will induce a varying magnetic field, which tries to block the movement of the device. And in this process, the coil needs to work against this resistive force. So say, for example, we turn our sharpener around, we need to work against the resistive force of the friction generated between the pencil and the sharpener. And here is the same thing. We rotate the motor around in the magnetic field loops, and then we need to overcome this force in order to generate a voltage. And in this case, we're changing the kinetic energy into electric energy. So energy is not free. Similar cases will be applied to the other things as well, like wireless charging. When the secondary coil is being cutting through with a changing total magnetic flux, when at one instance, when the current is flowing from upwards to downwards, and the secondary coil will try to create an opposite current, try to compromise its effect of flowing upwards to downwards. So it will try to produce a current from downwards to upwards to resist the motion in it. And the similar things apply when the current changes its direction when it's actually from downwards to upwards. The previous case is from upwards to downwards. We will generate opposing current, which is from it's pointing upwards. And in this case, the source current is pointing upwards, and the resistive current generated is going to pointing downwards. Okay, and this is probably the end of this video. We're discussing about the Maxwell equations and how the Maxwell equations can be related to 3 real-life scenarios about crosstalk, wireless charging, and power generator, which can be explained through this simple equation on the right-hand side. The right-hand side equation can be breaking down into 3 parts. The left-hand side part shows voltage. The right-hand side part shows the rate of change of total magnetic flux through a closed surface. Okay. Through a closed surface. Sorry for blocking it. And this minus sign indicating that they are opposing one another. Hooray! We've got one more concept understand it. Hope you like this video. If you do like it, don't forget to hit the thumb up and also subscribe to my channel for future updates. See you guys later. Bye bye.